Welcome back to The Explainer. Today, we're diving into integer manipulation. Honestly, it's a lot like taking apart and rebuilding a giant Lego set, just using some fundamental math operations. If you've ever stared at a block of code and wondered how a computer actually dissects raw numbers, well, you're absolutely in the right place. We're going to break down some core C++ logic today and look at exactly how we can systematically destroy and then perfectly reconstruct integers using just a couple of very basic mathematical tools. Here's our quick roadmap for today. We'll start with how to deconstruct numbers in code, move on to counting digits, then reversing those numbers entirely. After that, we'll tackle the palindrome test, and finally, we'll wrap up with the big takeaway on efficiency.
All right, part 1. Deconstructing numbers in code and the tools of the trade. Let's just jump right in and talk about how computers actually look at numerical data. You know, when we humans look at a number like 12,345, we process 5 distinct digits instantly, right? Our brains just automatically parse the 1, the 2, the 3, the 4, and the 5. But a computer? It doesn't see it that way at all. To a computer, that entire integer is just one solid, immovable chunk of data sitting in memory. So we actually have to teach our C++ program the physical action of dismantling that block, piece by piece, from right to left.
And to do that, we need specific tools. In base 10 mathematics, these two operators right here are literally your best friends. First, you've got the modulo operator, the percent sign. This plucks the last digit right out for us to use. When you say modulo 10, you're asking for the remainder of dividing by 10, which conveniently is always the final digit of the number. Then we have integer division, the forward slash. Since we're working with integers, dividing by 10 cleanly chops that final digit off entirely, but it leaves the rest of the number totally intact. So together, they just extract and discard over and over again. Moving on to part 2, algorithm 1, counting digits. Let's see how we can chop away at the problem. If our goal is simply to count how many digits are inside a number, our approach is pretty straightforward. First, we handle a quick edge case. If our number n is exactly 0, well, the number of digits is just 1, easy. For everything else, we set a counter to 0 simply because we haven't started deconstructing yet. Then we kick off a continuous loop that repeatedly divides n by 10. With every single division, a digit falls off and we bump our counter up by 1. We just keep doing this until n hits 0, which means there's literally nothing left to peel away. The real magic happens inside the while loop. As long as n does not equal 0, we add 1 to our count and we redefine n as n divided by 10. For every chunk we slice off, the counter goes up. So if you throw 12,345 into this, the loop runs exactly 5 times before n is reduced to 0. Boom! You're left with a final output count of 5. It's just wonderfully simple, isn't it?
All right, part 3, algorithm 2, reversing numbers, building it backwards. Now that we're pros at aggressively dismantling numbers, let's take that logic and build on it. Let's say we want to turn an input, like 1234, into 4321. Just counting isn't going to cut it anymore. We actually have to hold on to the pieces we're shaving off and put them back together. So we initialize a new variable called rev and set it to 0. Inside our loop, we bring in our modulo operator to extract the last digit. We do n modulo 10 and grab that piece. Now, and the order of operations here is absolutely crucial, we first multiply our rev variable by 10. This shifts everything to the left and creates an empty space. Then we add our plucked digit right into that new space. Finally, we do our standard integer division to chop the last digit off the original number.
What's really fascinating here is the opposing states of our two variables as the code executes. Think about it. Your original integer n is under constant attack. It's shrinking, just continually being divided by 10. But your newly initialized variable rev, it is aggressively growing. We're multiplying it by 10, essentially shifting its columns over and slotting in the freshly extracted modulo digit.
It is so cool to watch this physical action mathematically play out step by step. Take the input 1, 2, 3, 4. In the first pass, n gets chopped down to 1, 2, 3, and that discarded 4 is grabbed and tossed into rev. Next pass, n becomes 12, the 3 is grabbed. Rev multiplies the 4 by 10 to make 40, adds the 3, and becomes 43. This dance continues until n is completely destroyed down to 0, and rev builds up to 4321 flawlessly. It's just this beautiful, elegant transfer of data.
Okay, part 4. Algorithm 3, the palindrome test. This is kind of the boss level of today's concepts.
Let's see how we can combine the tools we've mastered to check if an integer is a palindrome. Now, a massive palindrome like 1,234,321 is instantly obvious to us, right? It reads the exact same forwards and backwards. But again, C++ doesn't have human intuition. It needs strict mathematical proof to confirm this. So how do we prove it? Well, we reverse the entire number and check if it perfectly matches the original input.
But here is the core twist, and honestly, this is a trap that catches a lot of people out. Because our reversal process relies on shaving our variable n down to absolutely 0, well, n is literally gone by the end of the loop. If we want to compare a reversed number to the original at the very end, we absolutely must safely store a copy of the original number first before we start our destruction sequence.
The logic here is just a direct upgrade to our reversal algorithm. We immediately declare a new integer, let's call it original, and set it equal to n. That safeguards our starting value. With n safely backed up, we can freely run our reverse loop logic, extracting those digits and building them into rev, while driving n straight into the ground. Once the loop finishes, we simply check whether rev is exactly equal to original. If they match, it returns true. You've got yourself a palindrome. Finally, part 5. The big takeaway on efficiency, speed, and space. We've solved 3 distinct coding problems using these basic math operators, but there's a hidden common thread here.
When you look at the complexity analysis, something remarkable stands out. Despite achieving totally different goals, counting, reversing, and palindrome checking, all 3 algorithms operate at the exact same blazing fast efficiency. Every single one of these functions has a time complexity of big O of log base 10n and a space complexity of big O of 1.
Let's unpack why this is so incredibly optimal. The time complexity is O of log base 10n, because the number of loop iterations is determined by continuously dividing n by 10. As the input gets bigger, the time it takes only scales logarithmically. That means it is astonishingly fast even for absolute monster numbers. And the space complexity? Constant, O of 1, because we're just peeling off base 10 digits mathematically and dropping them into a fixed variable. We aren't spinning up any new dynamic data structures like arrays or strings. Memory usage never increases no matter how huge the input number gets.
It is truly amazing what modulo and division can achieve together inside a standard while loop. By treating integers not as static, boring values, but as modular blocks we can mathematically pull apart, we get peak performance and flawless memory management. It really leaves you wondering, though, now that you know how to gracefully tear apart and rebuild primitive data, what other complex data structures can these simple building blocks unlock for you? Keep experimenting, and we'll see you in the next explainer.